Okay guys, today we're going to be covering transformations. So what are transformations? Well, if I were to graph a function of, let's say, a simple guy, like y equals x squared, transformations is what I would need to do to that function in order to shift the graph a few units in whatever direction. If I wanted to shift the graph to the right a bit, that would be a transformation. If I wanted to shift the graph down a bit, that'd be a transformation. If I wanted to make the function wider, that'd be a transformation. So with all that being said, let's get into the types of transformations. So I'm going to be doing these with respect to, let's say, f of x equals x squared is my function, okay? So it's important to understand how these work with respect to a function like this because it allows less ambiguity. And you're going to see what I mean in just a moment. So we're going to have two types of transformations. You're going to have translations, and you're going to have dilations. Okay? So let's take a look at exactly what those are. A translation would be on your graph moving your function left, right, up, down. Okay? That's a translation. So an example of a translation would be me taking f of x now equals x squared plus 4. This would be a translation up by 4 units. So now my graph would look like this. Consequently, I could translate it down by 4 units. And now my graph would look like this. Okay? So a addition or subtraction outside of the function provides a vertical translation. Okay? Where, by contrast, if I instead were to do an addition or subtraction inside the function, as in x minus 4 squared, that would translate me to the right, and my function would look like this now. In a similar sense, if I were to write this as x plus 4 squared, that would translate me to the left, and my function would look like this now. So that's the main thing to remember. If I add something to f of x outside of my x, that is going to be a vertical translation. And if I add something to x inside my x, that's going to be a horizontal translation. Now, something very important to keep in mind that kids often get messed up on is a negative inside the x function is going to push you to the right, where x plus 4 squared is going to push you to the left, as you can see demonstrated right here. Now, let's start talking about dilations. Okay, a dilation will make your function more constricted or less constricted. So a good example to use in this case would be f of x equals cosine x. So let's draw the standard form of cosine x right here. It would look a little something like that. Now, if I multiply my function by some number outside of the function, meaning I convert it to 2 cosine x, for example, my function experiences a stretch in the vertical direction. So now I'm going to be looking at something like this. You can see it's much more stretched out in the vertical plane compared to what we were looking at before. And the same is true if I want to compress it vertically. I can multiply it by 1/2, and that will compress it vertically. Now, keep in mind that the function will still oscillate at the same speed, meaning that the peaks and troughs will still occur at exactly the same locations, but they are just operating at a different height. So notice here above is the graph of cosine x, whereas below is 1/2 cosine x. Let me trace over that with red so we can greater see the difference. Okay? The minimum still happens at the same point. X-intercepts still happen at the same point. It's just cosine x is taller vertically than 1/2 cosine x. Now the other type of dilation we can see is the horizontal dilation. And the horizontal dilation is a multiplication inside the function. So f of x, again, we're going to observe cosine x, and if I wanted to perform a horizontal dilation, I would put it inside, as in cosine of 2x. So notice that there is a difference here. Now, when I multiply it by a big number inside the function, that results in a horizontal compression of the function. Whereas before, if I multiplied cosine x by a big number, it would result in a vertical expansion of the function. So when you're dealing in the vertical plane, a big positive number is an expansion. When you're dealing in the horizontal plane, a big number is a compression. Now let's take a look at what the graph of f of x equals cosine of 1/2 x might look like. That would be an expansion in the horizontal plane. So we might look like this now. Whereas prior, I was able to complete one full oscillation in my time, but now that I'm oscillating half as fast, I'm only able to complete 1/2 of an oscillation. So just to reiterate, multiplying by a number less than 1 inside results in an expansion. Multiplying by a number greater than 1 inside results in a compression. And the exact opposite is true in the vertical plane when you're multiplying outside the function. One more thing we have to consider here is going to be reflections. Okay? As a reflection, what you might be able to assume is that it reflects over one axis or another. So let's continue using f of x equals x squared, for example. So if I were to graph this, well, we all know what f of x equals x squared looks like. But now, what if I wanted to graph f of x equals negative x squared? Okay, this is a negative that is present outside of my function, as you can see by my parentheses. Therefore, this would be a reflection over the x-axis. We would invert it, and the new function would look like this. For the other example, the example of reflecting inside the function, we are going to consider f of x equals x to the third. Okay, if we draw that, so if now I were to draw f of x equals negative x to the third, now it's inside my parentheses, that would look a little something like this. What I did is I reflected it over the y-axis. I did a switcheroo like this. Okay? Okay, now let's do some examples, okay? First off, we're going to deal with f of x equals the absolute value of x, and that's going to look a little something like this. Okay? So let me give you a transformation. F of x equals the absolute value of x plus 3. What is that going to look like? We're going to use blue for this. Well, so first of all, our transformation is going to be inside our function, and that means it's going to be a horizontal transformation. That's going to shift us 3 units to the left. A lot of kids get tripped up on that. Horizontal translations mean positive to the left, negative to the right. What if I give you f of x equals the absolute value of 2x? So this is going to be a translation inside our function. So again, it's going to be a horizontal translation. And this is therefore going to be a compression, which will look something like this. Another very useful function, for example, is y equals rad x. Let's draw that first and foremost so we have something to reference. It's going to look something like this. Okay, and what if I told you to draw y equals 2 rad x? So this is going to be a transformation outside of our function, so it's going to operate in the vertical plane. Therefore, we're going to stretch vertically, and we're going to look a little something like that. Now, what if I were to give you y equals rad 2x? This is going to be a horizontal translation because it's inside our function. This is going to be a compression of the function, so it's going to look a little something like this. Now, something interesting to note here is that this is exactly the same as saying rad2 times rad x. So it's pretty much exactly the same as a vertical translation, but to a lesser degree, because rad2 is less than 2, which is apparent in the difference in the translation. You see, this one is not raised up as much as this one is. Next, let's consider some reflections, okay? What does the graph of y equals negative rad x look like? Pause the video right now and see if you can solve this, and then come back to me once you're done. Y equals negative rad x, since it's outside the function, is going to be a reflection over the x-axis, and we are going to look like this. How about the other reflection? What if we consider y equals rad negative x? That's going to be a reflection over the y-axis. So if we started like this, we are now going to look like this. We could also include a compression in addition to a reflection, in which we would look like this, with reference to our previous guy looking like this. So now we're going to deal with a pretty advanced problem which incorporates lots of different types of transformations. We're going to look at f of x equals 3 minus x plus 2 all squared. Okay? Now, the first thing I'm going to want to do for us to make it easier to visualize is I'm going to say this is equal to negative x plus 2 squared plus 3. All I did was I pulled the 3 and I moved it over here because addition is commutative. So now what I need to do is I need to identify what is the general function I'm dealing with here. I'm dealing with something that is generally an x squared, okay, as you can see right here. Okay, so that's going to be the first thing I do when I graph the function. I'm going to graph a parabola. Now, the next thing I notice here is that my parabola has a horizontal shift associated with it. Therefore, it's going to be moved, in this case, 2 units to the left. So we're now looking at this point as opposed to the origin. We're also noticing that we are going to be shifting up by 3 units. So now my origin, or vertex point I should call it, is going to be roughly around here. And then I have a negation or a reflection outside my function, which means it's a vertical reflection. So I'm going to be reflecting across the x-axis, and my final parabola is going to look something like this. Okay? That is how we graph functions based on their transformations.